In this lecture, we will mainly discuss classification of ODEs, which will be essential later on when we're trying to develop solution strategies for various ODEs. Now, just to summarize what we were discussing in the previous lecture, a differential equation, under a differential equation, will understand any equation that contains an unknown function along with its derivatives. And here I listed some examples of ODEs of differential equations. So you see that all of them are equations, all of them involve derivatives. And a couple of immediate classifications will emerge from what we see here. So one classification is according to the type of derivatives that appear in an equation. So here it's a usual derivative with respect to the one variable. Derivatives with respect to one variable, derivatives with respect to one variable. So y is a function of x in a, b, and c. But in D, we see a function u that depends on x and y because we're taking partial derivatives with respect to x and y. So according to the type of derivatives that appear in a given equation, we'll classify a given equation either as an ordinary differential equation, if you see ordinary normal derivatives, or as a partial differential equation if you have partial derivatives. So the equation that is circled is the only partial differential equation in this list because it is the only one that involves partial derivatives. So everybody A, B, and C here are ordinary differential equations or ODEs, and D is a partial differential equation or PD. And in this course, we're lucky that we don't need to worry about PDs because we're only going to look at ODEs. Clearly, PDs are going to be much more challenging to solve because you have more than one variable. Okay, so that's one classification. So for the rest of this course, we're not going to worry about things like D, and instead we will try to figure out strategies of how to solve A, B, and C, and other similar equations. Okay, so now what else can we see in all three of these equations? We can see that the highest power of a derivative that appears in RODs is different. In case A, the highest power is 1, so highest order of a derivative is 1. For the equation B, the highest derivative that appears is y double prime, and for C, it's the fifth derivative. And the second classification that we're going to consider is this then. We're going to classify each ODE according to the order of the highest derivative that appears in that ODE. So for that reason, equation A is going to be a first order ODE. Equation B is going to be a second order ODE because it has a second derivative. And the highest derivative in C is fifth one, so this would be a fifth order equation. Now, what does order of a derivative have to do with anything? So for one, clearly the higher is the order of a derivative, the more complicated equation is going to be, because in order to solve the equation, I showed you a couple of examples last time, solving an ODE will typically explicitly or implicitly involve integration. So if I want to solve the first order ODE, for instance, to undo the highest derivative, I'll have to integrate once. And if I integrate once, then that will produce an unknown constant. In order to solve an equation similar to B, to get rid of y double prime, I'll have to integrate twice. And that means that each of these integrations will produce an unknown constant. So integrating the equation B, the ODE B, should give me two unknown constants. And likewise, integrating or solving the equation C will involve 5 integrations, so it will produce 5 unknown constants. So what we can deduce from this is that what would we expect from a solution of the nth order ODE? We would expect that the solution of the nth order ODE will depend on n unknown constants. So if it depends on n unknown constants, it doesn't matter how many unknown constants are there, that immediately implies that in general, solution of an ODE is not unique. Just like an antiderivative is not unique, you have infinitely many antiderivatives distinguished by the value of an unknown constant. Is the same thing here, that any ODE should have infinitely many solutions. And those solutions are going to be parameterized by the unknown constants. And again, the number of constants, unknown constant that is involved in a solution of the nth order equation is going to be exactly the same as the order of the equation, and it is n. So to make this somehow more clear, let's do an example. So I want to, first of all, classify this equation y triple prime equal to sine x. And second, I want to solve it if I can. So let's think of a classification. So this is y triple prime equal to sine x. You see only ordinary derivatives, so this is an ODE. And the highest order of a derivative that appears is 3. So this must be a third order ODE. Okay, so would I be able to solve it? The answer is yes, pretty easily, because if I know that y triple prime is equal to sine x, then I can compute y double prime simply by taking antiderivative of y triple prime. Y triple prime is sine, so I need to take integral of sine. Integral of sine is minus cosine plus a constant. And I'm going to call this constant C1. If I know y double prime, I should be able to compute y prime. So what is y prime? Y prime is an antiderivative of y double prime. Y double prime I know from the previous line, so I need to integrate this y double prime. Integral of minus cosine is minus sine. Integral of C1 of a constant is C1x, and the integration results in a new constant of integration, C2. And rinse and repeat. So what is y? Y is an integral of y prime. Y prime is a thing that I've just computed. So I take integral of that. Integral of minus sine is cosine. Integral of c1x is c1x squared over 2. Integral of a constant c2 is c2x. And because I'm integrating, I need to add another constant, c3. So at the end of the day, I solve the third order equation. And this third order equation has a solution which depends on 3 unknown constants. We're going to call a solution like that a 3-parameter family of solutions, right? Why is it a family of solutions? Because this expression encodes not one solution, but infinitely many. And I can prescribe any value, any set of values, C1, C2, C3, no matter what these constants are, what the values of these constants are, the result is a solution. So if all of the constants, for example, are 0, then cosine of x is a solution. If C1 is 1, C2 and C3 are 0, then cosine x plus x squared over 2 is a solution. C1 and C3 are 0 and C2 is minus 2, so cosine x minus 2x is a solution. So solving an ODE involves actually finding infinitely many solutions of that ODE. So just to summarize in general, then what we expect is that any nth order ODE should possess an n-parameter family of solutions. Okay, let's do an example. I want to verify that the function y equal to c1 cosine of x plus c2 sine x that this function forms a two-parameter family of solutions of a second order ODE, y double prime plus y equal to 0. Already I can see that this is a two-parameter family of functions because this expression defines infinitely many functions that are distinguished by different values of C1 and C2. So the only thing that I need to verify is that this two-parameter family of functions actually gives me always a solution for any value of C1 and C2. It gives me a solution of the ODE. So I need to verify that this y will solve this ODE regardless of what C1 and C2 are. Now, how do you solve an equation? You simply have to substitute a solution into the equation, and the equation will become an identity. Now, but before I substitute y into the ODE, I need to figure out y double prime, right? Because at the end of the day, I will be adding y double prime to y. Okay, so if y is c1 cosine plus c2 sine, then y prime is minus c1 sine plus c2 cosine. And y double prime, taking derivative again, is minus c1 cosine minus c2 sine. So if I substitute into the equation, I'll get minus c1 cosine plus c2 sine minus c2 sine, and y is plus c1 cosine plus c2 sine. So these cancel each other out. At the end of the day, you get 0. So that means that for any c1 and c2, ry is a solution, and so therefore c1 cosine x plus c2 sine x is a one-parameter family, is a two-parameter family of solutions of y double prime plus y equal to 0. Now another observation is, so if this guy solves my equation for any value of c1 and c2, then I can choose, for instance, c1 equal to 1, c2 equal to 0. If I do that, I recover the function y equal to cosine of x. And because for any c1 and c2, y is a solution, that means that cosine of x is a solution of my ODE. Now, this solution does not involve any unknown constants. And for that reason, we're going to call it a particular solution of our ODE. So then other examples of particular solutions are going to be given by different choices of C1 and C2. I can make C1 0 and C2 1. This will give me y equal to sine x. I can make C1 1 and C2 1. That will give me y equal to sine x plus cosine x. C1 is 2, C2 is minus 1, gives me this. So there are infinitely many choices of particular solutions to my equation, right? Again, distinguished by the values of C1 and C2. I can even do the following problem. Let's say I want to find a particular solution, not just any particular solution of y double prime plus y equal to 0, but I want to specify some additional conditions that y of 0 is equal to 0 and y prime of 0 is equal to minus 1. So I'm specifying two conditions. I know that my family of solutions contain two unknown constants, so hopefully I will be able to determine the constants based on these conditions. And if I do, then I will find a solution of my ODE which satisfies these two additional conditions. So I already know that C1 cosine x plus C2 sine x solves my ODE regardless of what C1 and C2 are. And now I need to figure out what are C1 and C2 that produce these values for y of 0 and y prime of 0. And so I need to figure out y prime. So if y is like this, y prime I get just by taking a derivative. So then what is y of 0? Y of 0 on one hand is 1 because that's what I want it to be. But on the other hand, it is this expression here with x replaced by 0. So you get c1 cosine 0 plus c2 sine 0. Sine 0 is 0, cosine 0 is 1, so this is c1, and therefore c1 must be 1. On the other hand, y prime of 0 I want to be minus 1. But what is y prime of 0? It's a value of this expression, 0. So it's going to be minus c1 sine 0 plus c2 cosine 0. Sine 0 is 0, cosine 0 is 1, so this is c2. So this indicates that c2 is equal to minus 1. So I found c1 and c2. So then I found a particular solution of my equation which satisfies these conditions. Later on, we will see that we call these conditions initial conditions. And this is sort of related to one of the examples that I showed you in my previous lecture. Remember, we were talking about the mass falling to the ground, mass released from some height. In order for me to figure out the position of a mass, what I had to do is to integrate a second Newton's law, which involved integrating acceleration. Acceleration is the second derivative of position, so that means that there I was solving a second order ODE, which should have given me two unknown constants. So in order to determine these constants, I had to know where my mass was in the beginning and what the initial velocity of the mass was. So this is kind of an analog of that same problem, that you're prescribing initial, say, position, initial velocity, and the equation itself is some sort of a statement about acceleration. Don't take this literally, but that's sort of a background idea here. All right, so let's return to theory for a moment. So in general, if we are looking at the nth order ODE, it's nothing but some sort of a function which involves x, y, and all derivatives of y up to n. So f is just some function of actually n plus 2 variables, right? Because we start from y to, we have x, y, and we have derivatives from y from 1 to n. So there are n derivatives plus 2 variables x and y. So this is some function of n plus 2 variables. So for example, capital F might have this form or that form. This would be, right, so just on the left-hand side, you have any function of x, y, and derivatives of y. This, by the way, is a second order ODE. This one is a first order ODE. Sorry. All right, so now these ODEs can be solved for the highest derivative. So the highest derivative is 2 in this case. Highest derivative is 1 in that case. If I solve for highest derivatives, the equation will have these respective forms. Now, if your ODE is solved for is written in such a way so that it is solved for the highest derivative, then we will say that these equations are going to be in a normal form. So this first equation in a normal form looks like this. The second equation in the normal form looks like that. And so any ODE that looks like this is going to be an ODE in a normal form. All right, so the final piece of classification that we're going to discuss in this lecture is classification by linearity. And at this point, this is probably not going to be very clear why things look in this particular way, but you'll get an idea later on when we actually discuss these linear equations in length. So any equation of the form that is written here, so I'm writing nth order ODE, and it has the following form. It's a function of x times the nth derivative plus another function of x times n minus first derivative, and so on, plus another function of x times first derivative, and then lastly, one more function of x times the function y itself. And this is all equal to some other function of x. So whenever equation has this form, it's called a linear equation. Why linear? Because y and its derivatives appear in the equation in a linear way, right? So dependence on x can be very complicated, but dependence on y and its derivative is always a linear function. So if an equation is in this form, then it's a linear equation. Any other equation is going to be called a nonlinear equation. So just giving you a few examples. Looking at the first example, this is a second order equation. And I see function of x times y prime, another function of x, y double prime, another function of x times y prime plus 1, which is a function of x times y equal to sine x. That fits this form here. So we get a second order linear equation. Function of x times the fifth derivative, function of x times the second derivative, minus plus function of x times first derivative equal to 0. That's a fifth order equation. And of course, again, derivatives appear in a linear way, so this must be a linear ODE. Similarly, this guy, or not similar actually, look at this guy. What do we have here? We have x times the second derivative, that appears in a linear way, but then I have sine x times y squared. So y squared is not a linear function. So that means that this equation now is nonlinear. And the same thing in the last example, because here, for instance, I have a product of y and y prime. If I have a product of y and its derivative, then again, this is not linear. This is not in this form. All right, some more examples. I want to verify that the function y equal to x cubed solves this equation, and I want to classify the ODE that I got. So let's classify the ODE first. It's a second order. It looks like function of x times y double prime plus another function of x times y prime plus another function of x times y equal to 0. So this must be a second order linear ODE. Now, if I want to check if x cubed is a solution, I need to substitute it in. So in order to substitute it, I have to figure out second derivative and the first derivative. If y is x cubed, y prime is 3x squared, y double prime is 6x. So substituting, I get x squared times 6x minus x times 3x squared minus 3 times x cubed. Combine this, you get 0, so that means that x cubed is a solution, right? Because you get an identity. All right, and then the last example today is the following. So it's a similar example. Again, I have an ODE, and I'm given a function, and I want to verify whether this function is a solution of the equation or not, and I want to classify the equation. So the highest order of a derivative that is involved here is the first one. So this must be a first order ODE. It's not linear because you see the product of a function of y and a function, you see a product of y and y prime. And now in order to verify if this guy is a solution, what I need to do is I need to substitute it. But in order for me to substitute it in, I need to figure out the derivative. And here I have several choices of how to do it, and I want to follow this one. This function here, is specified. You remember that you can specify a function implicitly and explicitly. Explicitly, if y is given as a function of x, and implicitly, if you have some equation that connects x and y. So in this case, x and y are related via this equation. This is not solved for y, so it means that y is specified implicitly. And if it is specified implicitly, then you might recall from Calc 1 then that you can compute a derivative also implicit. So I can compute a derivative implicitly and then plug in and see if the equation is satisfied. Okay, so how do we take a derivative implicitly? So remember, you need to review how to do it. What you need to do is to take the equation, the circle equation here, then remember that y in this equation must be a function of x, and then take derivative of both sides of the equation with respect to x. So that's what I'm doing here. Then derivative of x squared plus y squared must be by properties of a derivative. Derivative of the first guy plus derivative of the second guy equal to the derivative of 1, which is clearly 0. So then derivative of x squared is 2x. There is not much that one can say here. What is derivative of y squared? So y is a function of x squared. So in order to take its derivative, I need to use a chain rule, right? So it's a derivative of the outside function, which is quadratic. That gives me 2y, times the derivative of the inside function with respect to x, and that means times y prime. And the whole thing is still equal to 0. And now you solve this for y prime, and you end up with this expression. So you might recall also that when you take a derivative implicitly, because originally you did not solve for y in terms of x, then implicit derivative will give you y prime not just in terms of x, but in terms of x and y. Actually, this circle expression already means the following. You have y prime equal to minus x over y. So that by itself looks like an ODE. Looks like an ODE of the first order. And in fact, it is written as y prime equal to something. So that's a first order ODE in a normal form. So immediately I get that my implicitly defined function y solves this circled ODE. All right, so now let's see if this thing satisfies the ODE that I gave you in the beginning. So I take this y prime and I substitute it into the left-hand side of the equation. So y prime is minus x over y. So you simplify minus x plus x, and this is equal to 0. So that means that our function is an implicitly given solution of our equation. Now, in fact, this implicit derivative, the equation ODE given by this implicit derivative, is exactly the same as the equation written here. And I can easily see that simply by multiplying by y and adding x to both sides. All right, so in the next lecture, we're going to talk about how do you find particular solutions of ODEs with initial conditions.